Excuse me.
I wonder if it was recorded.
I was quiet enough to the point where I don't think the camera's going to be able to pick it up, but here's hoping.
I see. All right, let's see here. If you can add a date to the top of this, would be great.
I can do that.
And I will begin with a word of prayer. I can sort of still talk, so. Dear Father, we thank you for this day. Thank you for these students. Just ask you to bless this class today. Help us to understand a little bit more about your creation together, Lord. In your name I pray, Lord Jesus. Amen. Excuse me. All right, so, lest I forget, we should talk a little bit about well, tell you what, I'm going to circle back and talk about that some other day. I'll make a mental note for myself. I need to come back and talk to you guys about energy and power with respect to capacitors and resistors. I'll try to do that Monday or something like that. But today I want to talk about a little bit more about, circuits. And more specifically, I'm talking about DC circuit analysis. And so I just want to lay down the rules for you guys and try to explain how we go about solving these sorts of problems. The main tool in our arsenal that we have to keep in mind is Ohm's law, right? So Ohm's law, well, that's one of the things. Ohm's law says that the voltage is equal to I times R. To be more specific, this is the voltage dropped. And this is the current. So that's dq dt, the charge passing through the, and this is the resistance. Remember last time we talked a little bit about resistance. You could write as resistivity times the length divided by A, I think. So there's a formula for finding the resistance if you happen to know the resistivity and the physical dimensions of your resistor. But I really should put that in parentheses because we're probably not even going to come back to that. Certainly not today. Just side comment, okay? Side comment. So one thing we must keep in mind is Ohm's law. This relates the current flowing through a resistor to the voltage which is dropped across the resistor. The other thing we have to keep in mind is that charge is conserved, all right? And so what that actually amounts to for us is that all the currents that come into a node and come out of a node, like the net amount of current coming into a node has to be zero. Like whatever, in other words to say that is the sum of the currents going into a node must be equal to the sum of the currents going out of the node. You can't have a place where two wires come together and it's somehow just magically creating charge. Like that's impossible. So we know that current is conserved. So there's two basic laws which are Kirchhoff's. I can't remember how to spell Kirchhoff. This is probably wrong. Put some quotes around that. I got it right? Yeah, what do you know? 1H. Oh, that was a K. So it just, see, I was wrong. So it's like this. Kirchhoff? Oh, okay. So Kirchhoff voltage, and he also has the current law. And so those are the things we need to learn how to implement. So rather than try to explain to you them abstractly, we're going to illustrate by examples. And along the way, we're also going to discover another concept, which is that of equivalent resistance. So let me look at my first example here. And so I'll be introducing some things as we go. This is an ideal voltage source. So I'll use E. People use this E for It's a very outdated term, but electromotive force. It's not a force, it's a potential. So it's like a doubly bad term, you know? It's confusing force and potential energy. It's really kind of sad as a term. But anyway, EMF, electromotive force, but we'll just think about this as an ideal battery. So an ideal battery is one for which it always puts out a voltage that's fixed, all right? A fixed voltage independent of the current you're drawing out of it. So these things don't exist in reality, but they do exist in physics tests. So here you go. This is a battery with voltage E. And then, we'll start out really, really simple. Here we go. This is like the simplest possible stupid circuit I can think of, R. This is so simple, it's just dumb. And so, all right. So we start out, I usually put a minus to a plus like that. So we're going up voltage E, and then the current flows like this. And I say current, I mean conventional current. And then as that goes through here, there's a voltage drop, so plus to minus. So Kirchhoff's voltage law, which we'll say KVL, it just looks like E minus IR equal to 0. So the way this is working, guys, is we're going in a loop like this. All right, and you notice the difference. Minus to plus, I add. Plus to minus, I subtract. All right, so that's Kirchhoff's voltage law. And Kirchhoff's current law is harder to write down because there's no node. Okay. Sorry, there's no Kirchhoff. So anyway, we just have E equals IR. So this is a very dumb example. So, you know, the current in the circuit would be E over R. Great. Let me make a less dumb example. That example's too simple. Sometimes too simple an example is a bad thing. Let's put two resistors into play here. So I'll keep with my ideal voltage source E, and I'll put an R1, and I'll put an R2. All right. Excuse me. Again, I'm going to put my plus minuses to just kind of tell you what's going on here. Minus plus, and I imagine the conventional current flowing like this, and then it flows like that, and there's a voltage drop, and another voltage drop as that current I goes through there. Kirchhoff's voltage law now tells me the following. Tells me E minus IR1 minus IR2 equals to 0. Again, I pick a point, maybe this point right here, right? And then I'm going in a loop back to where I started to write this down. I add the sum of the voltage drops around the loop like that. And so what does this tell us? This tells us that the current, we do algebra, right? E equals to I times R1 plus R2, right? So the current is equal to E over R1 plus R2, right? And what does this show us? This shows us that if you want to think about this as like a black box, right? If you want to think about this in terms of an equivalent circuit, this is the same, right? It's the same as if I was to say replace this with an equivalent circuit of the same voltage, right? And then R equivalent. So this would be E over R equivalent. What's R equivalent? R1 plus R2, yeah. So this is kind of embarrassing. Well, it's not embarrassing, it's just the way the world works. For series, so the series resistance works like parallel capacitors, right? Remember we had that if capacitors were in parallel, then the equivalent capacitance we get by adding? The opposite seems to be true here for resistors, right? So it would be cool if when we looked at parallel resistors, we found that they followed the same rule as like series capacitors. And that is in fact what's going to happen. Let's see how. So example 3, we take a voltage source, E, right? And this time we're going to put 2 resistors into play here. But this time in parallel. All right? And I think maybe this, oh, by the way, this example 2, again, we couldn't really see Kirchhoff's current law at all, could we? There was no node to speak of. But here, we've got a node right there, right? A place where wires come together. So it serves us to denote some currents. Like here, I'll call this I1. Actually, let me just call that, I'm going to call that I3, weirdly enough. Okay? Because it occurs to me, I'd like to say that the current going through this one is I1, and the current going through here is I2. All right, and so it's going to plus minus, plus minus. If the current is flowing through the resistor, the voltage drops in the direction in which the current's flowing. That's the way I think of it. So Kirchhoff's current law, let me give this label A. So the Kirchhoff's current law, KCL, at A, what's it tell me? What's the relation between I3, I1, and I2? Uh-huh. I heard an I3 equals I1 plus I2. So can we take a vote on this? Who else agrees? All right, that's a consensus. That must be true. No, this is true. So this is the current in is I3, right? And the current out is I1 plus I2. So that's Kirchhoff's current law. The currents in have to be equal to the currents out. Or you could say the sum of the currents into the node is 0. So if I wanted to look at it that way, the sum of the currents into the node, it would look like this, right? I3 minus I1 minus I2 equals to 0. There I'm saying the sum of the currents into the node. See, if I do that, I1 and I2 are going out of the node, so I have to do minus them to consider them as inward currents, right? But anyway, you can write down I3 equals I1 plus I2 if you like. That's fine. And then what else can we say? How about this? I've been doing Kirchhoff's voltage law. I guess I can do that again. So we can do this loop right here, right? So the Kirchhoff voltage law for loop 1 would give me E minus I1R equals to 0. So that's the first loop there. And I can also do another loop, which I'll do in orange, like this, right? Start here, go over here, go down, and then come back like that. So KVL2, what's that give me? What's that? Which I? There's an I1, an I2, and I3, so there's no I. I2? Okay, yeah, I2. And what could you criticize about my equation above? Yeah, which R is that, right? That's supposed to be what? R what? R1, yeah. So another way to say this is that E has to be equal to I1R1, and E has to be equal to I2R2. And honestly, guys, I don't, to complete truth in advertising here, I don't usually use loops to come up to those conclusions. My typical way of operation is I just look at the circuit and I go, okay, so if if I define a ground, well, I'm going to do this example again with the other way of thinking next, but let's finish this way of thinking, and then rather than making this example super messy, let me just do it the other way after we're done with this. All right, so we've got 3 equations, 3 unknowns, right? I'm really interested in what I3 is. So can you guys help me? How do I solve for I3? Well, I've got I3 is I1 plus I2, right? But I can solve KVL1 and KVL2 for I1 and I2 respective, right? Yeah, equals E over R1 plus E over R2, right? Which is E times 1 over R1 plus 1 over R2. And on the other hand, this is also equal to E over R equivalent, right? So if we say this is the same as the corresponding circuit, E with the equivalent resistance, right? And assuming that, the same current is going to be flowing, so it's an equivalent. In other words, we're trying to think about all of this as being a black box, if you understand. Like, think about this, all of this mess here, as just being this. We don't care about the internal details over here. It happens to be it's a parallel combination, right? And if that's the situation, this tells us REQ is what? It's 1 over the sum of the reciprocals, also known as the product of the resistances divided by their sum. So that's how you find the equivalent resistance for a parallel combination. It's just like capacitors rather, in series. All right. So let me, any questions? So let me just take another look at example 3. Come see for pi before you leave, heart? What? Fascinating. Erase this here. All right, so there's, I think there's like basically 2 main strategies for coming up with equations to fix the voltage in circuits. And those 2 strategies, to summarize briefly, would be use the sum of the voltages around a loop is 0. That's Kirchhoff's voltage law. But the other strategy is just to calculate absolute voltage given a particular reference point. So I'm going to use the reference point idea for example 3 revisited. And it's not really much different. So here's E. Here's my first resistance. Here's my second resistance. You'll forgive me for not putting numbers in, but numbers would just distract us at this moment. We'll put numbers in before too long. Don't worry. I promise. So what I do is I just say, okay, well, this is going to be, I'm going to define voltage equals to 0, where ground is. All right? And once I do that, once I've specified where the voltage is 0, and I could specify the voltage is 10 volts or something if I wanted to, whatever. But that would be weird. Most people specify voltage to be 0. And so once I've done that, I can calculate the voltage at other points using Ohm's law or the definition of the circuit element. So like here, since this is an ideal voltage source, that means that this point right up here, A, has to be, this is A. So the voltage at A has to be E. Tell you what, let me make it less weird. I'll make this 9 volts. It's a 9-volt battery. All right, it just became real. Like it? Let's make it more real. 4.2 volts. There you go. That's much more real. Because that's what? The voltage of a typical what? You guys don't know? What's 4.2 the typical voltage of? AAA, AA. You guys don't know? Huh. Interesting. Well, look into it, see if you can figure it out. So 4.2 volts. And did I remember it wrong? Is it 3.5? Daniel, what is it? What? Oh, 3.5. I'm an idiot. There, does that make it better? Now what am I talking about? No, not AA. No, 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 no. No, not a deep battery. No, is this wrong? What was it, Daniel? What? Well, so I was right, 4.2. Ah. This is the voltage of a typical lithium-ion cell. Lithium-ion. So anyway, so if that was a typical lithium-ion, I can't say words today. So if the voltage is 0 here, 4.2 up here, right? And if it's 4.2 volts here, it's also 4.2 volts here. It's also 4.2 volts here. Because this is all at the same node. So when it's physically connected with a wire with no circuit elements between it, same voltage. And then, once I know that, and see, the thing is, you know, if this is I1 and this is I2, as I've, did over there, I've got that the voltage up here is, 4.2 volts, and I wouldn't almost never put another label, but VB is equal to VA because they're in fact the same node. So if I start at 4.2 volts and then down here I've got, let me call this point C. VC is 0 volts. So VB minus VC has to be equal to I2 times R2 by Ohm's law. Right? So my point is we could also directly come to the conclusion that like 4.2 volts has to be equal to I1 R1 and has to be equal to I2 R2 if we use this notion. Uh-oh. All right. So let me try another example here. Yeah. Well, let me do the easy part first. Let's work out the equivalent resistance of something a little bit more snazzy. So, example, yeah. Oh, 4. Thank you, thank you. I need glasses. Let's see here, I couldn't see what you're doing. Isn't that sad? Like your hand is all blurry to me. It's pathetic. Anyway, example 4. So suppose you've got this system of resistances. Do-do-do-do-do. Do-do-do-do-do. Woot, woot. And we'll say R1, R2, R3, R4, all right? So this would be the same as what equivalent resistance? Sorry, my resistance symbols are getting more and more sketchy. But you guys tell me, what's the formula here? Oh, here, let me show you a symbolic. Here's a way we can do it symbolically as like an intermediate. So let's talk about this. We've got what? R1 paralleled with R2, right? In series with R3 plus R4. I mean, we can justifiably use plus for the series. You know, I mean, if I wanted to think about it more systematically, it's like this series combination in series with that parallel combination, if you'll accept my notation. But then that's R1, R2 divided by R1 plus R2 plus R3 plus R4. And there you go. That would be it. Let's do another one of these equivalent resistance problems. These are fun. Suppose we have, let's see here, example 5, I guess. Suppose we have R1, R2, and then over here, R3, R4. So this would be the equivalent capacitance. How would we work it out here this time? We do what? We do R1 plus R2, that series combination, right? Paralleled with R3 plus R4. If you'll allow me this notation. It's probably bad mathematics, but forgive me. This would be what then? This is, we take the product, R1 plus R2 times R3 times R4, plus R4 rather, and divide by the sum of the resistances. Hey, that's kind of cool. Neat. Yeah. All right, well, we can do more of these, of course, but I think it'd probably be good for me to get back to circuit analysis, and let's try to work through a particular circuit step by step and see if we can answer some questions about it. Excuse me. So I will make up a circuit for us. Hopefully it'll be a reasonable circuit. So 20 volts, and suppose I've got a 10 kilo ohm resistor here. All right, and then I'll put a parallel combination over here. All right, and what do you guys think I should put over here? Maybe we'll do, what's that? Okay, 50 kilo ohms, and I'll put another 50 kilo ohms right here. All right. So if I do that, let me show you how we can use equivalent resistance to figure this circuit out. So we're interested in a few different things. Our goal is to figure out what is I1. We'd also like to know what's the voltage here at point A. I'm going to define V equals to 0 right down here, okay? The ground, I'm going to say V equals 0 there, relative to that choice of voltage. What's the voltage at A? And then let's see here. Yeah, and I also want to know what's the current here. All right. Okay. So those are the questions I'd like to answer. Voltage at A, the current one, and the current two. All right. So I'm going to take the one the problem we're given, and I'm going to replace it with the equivalent resistance. What's the equivalent resistance for these three? 35 kilo ohms, right? We got 10 kilo ohms plus the parallel combination of 50K and 50K. Now, if you take two resistors that have the same resistance and you put them in parallel, it just halves them, which is probably how you did that, right? No? Oh, okay. Well, you just knew.
I'm in NG211.
You're an NG211, so you just know. You're not. You can't even think. You can't even explain the thought process anymore. It's just like,
Yeah.
you wake up in the morning, you're like, 15K ohms, like that. It's like you dream of resistance. Okay. Anyway, so yes, this is 10K ohms plus 25K ohms. So I regret not making the voltage, the battery at 35 volt, but it's okay. It is what it is. So we got 20 volts here, and our equivalent resistance, like that. Oh man, whoa, 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 what's happening here? That's not good. It's not good. It's not good at all. Whoa, strike that from the record. Good grief. Oh, I'm hoping I make it to the problem session today, guys, but I don't know. So 35 kilo ohms. Good, right, work. All right, so the thing is, the same current will flow through this 35 equivalent resistor as would flow through I1, right? This will immediately tell us what I1 is. Yeah? So by Ohm's law, I1 is equal to 20 volts divided by 35 kilo ohms. I say, but I don't, I say one thing and I write a different thing. It's really, really annoying. So what's 20 over 35? 0.57, roughly. So 0.757. By the way, something to notice, 1 over kilo is milli. So that's 0.57 milliamps. All right. So that's one of my questions. There we go. We figured out 0.75 milliamps, right? And then here's the kind of analysis I was talking about. So we now know that there's 0.75 milliamps flowing through there, right? So if I go up here, I go plus, minus. I can write down the following. I can say, oh, okay, well then, by the way, this voltage right here is 20 volts, right? Because we start at 0, the absolute voltage there is 20 volts. If I want to know the absolute voltage here, I can take the voltage here at this node and subtract the voltage dropped across that resistor, which I know now. So I can say the voltage at A has to be equal to 20 volts minus 0.57 milliamps times 10 kilo ohms. Now the milli and the kilo are natural enemies, and that just gives you 20 minus 5.7, which is otherwise known as 14.3 volts. 14.3 volts. Yeah, well, that I can do. But, and then, this one I can't do in my head. I2, well, what's I2 going to be? 0.285. Oh. Oh, man, you're right. Duh. The Kirk has pointed out that since these resistances are equal, the current's halved. Right? By symmetry, half the current has to go here, half the current has to go there. So if my I1 is 0.57, divide by 2, you get 0.0285? Yeah. So we got to have 0.285 milliamps this way, and likewise 0.285 milliamps that way, because that's half of the 0.57. That's the one way you could do it. That was actually not the way I wanted to do it. The way I wanted to see that is I2, I'll do it over here, is equal to the voltage at A divided by 50 kilo ohms. which is, 14.3 volts divided by 50 kilo ohms. And that was what I was saying I couldn't do in my head. That's what I meant I can't do in my head, because I forgot the obvious symmetry argument. Duh. I should have made it more complicated. Oh well. Which is going to give us what? 286. You're cheating. 285 milliamps. Of course, we could all be wrong because I'm still trusting. All of this is based on the alleged value of 0.57 milliamps here. If that's something else, then we're off according to that. Does that make sense? Now, this method I'm using this is sometimes called the Thevenin. Is that right? Thevenin. You don't have a name for it? You don't have a name for the equivalence resistance? Well, Thevenin's theorem says that you can replace a bunch of resistors like this with an equivalent resistance and solve it like this. This is not always possible, though. If you've got more than one voltage source, then you kind of have to do the algebra. But if there's just one voltage source like this, then you can kind of just always convert it to the equivalent resistance, find the net current coming out of your voltage source, and then work your way backwards to any other information you need. This is really nice because it means you don't actually have to solve the system of equations that would come from Kirchhoff's voltage law, Kirchhoff's loops. I know this very deeply because I have a 2-year degree in electronics engineering technology, and we didn't know linear algebra. So our only method for solving circuits was this. This is all we knew. If you gave me a problem with two batteries in it, we couldn't solve it because we didn't know linear algebra. Well, I mean, it would have to sort of be a contrived system that was simple enough that we could still solve it. But anyway. Let's see here. All right. So we will work more complicated circuit problems. Like, we're going to be on this for like a day or two. Probably at least one more solid day, I'll just do circuits. All right. And then we'll probably flip back to like RC circuits. But this is not the end of this. I do need to do a more complicated example that takes us like a full 30 minutes to work out. We do all the algebra and all that. These are more complicated in general. All right. And you're going to have to learn how to solve linear systems. Like, how do you solve 3 equations and 3 unknowns with ugly numbers in it? Like, that's something we're going to have to learn how to do, if you don't know already. So in the time that remains, let me just talk about power, since I got a little bit of time here. Power. So we have the voltage is equal to I times R, right? Well, that means that the voltage is equal to dq dt times R. Let's see if I can say anything here. Man, it's not what I want to say. There's something obvious I want to say here. It's not coming to me. Oh, yeah, duh. Not wrong, just not helpful. So if I have a resistance and I've got, voltage here at D, voltage here at A, right? And I've got the current I flowing through resistance R. We know that VB minus VA over Q, right? Sorry guys, I'll get it eventually here. So this times dq should be the potential change in potential energy that you get, right? If you think about a little bit of charge flowing through this resistor, the potential energy, so remember, voltage is potential energy per unit charge. So if I have a charge of dq flowing through the resistor, the change in potential energy is du. Are we all in agreement? I hope we're in agreement now. So divide this by dt. What do you get? So we get the change in energy per time. This is power. So therefore, the power is equal to, what's this? What's dq dt? Current, right? So we have the change in voltage times the current is equal to the power. And then, of course, what do we typically use here? So oftentimes we just like to write IV and just let V be the voltage drop. So the power going through a resistor, rather not the power going through, but the power developed by a resistor, I should say, is the current times the voltage. And there are there are two other formulas, right? Because Ohm's law says what? V is IR, right? So I can also write this as I times IR, also known as I squared R, right? I can eliminate the voltage. And my other choice is eliminating current. If I solve for I is what? V over R. So if I plug that in here, I get V squared over R. And there you go. Those are the three important formulas to know about the power developed by a resistor. The current times the voltage, and then you also have current squared times resistance and voltage squared times resistance. I'd like to point out that my derivation of the relation of power and current has nothing at all to do with Ohm's law, right? So I was talking about a resistor here, but truth be told, this is a general truth of circuit elements. The voltage dropped times the current through is equal to the power dissipated in that element. So this is not just like the IV formula, it's not just for resistors. But in the case of resistors, it's also equal to I squared R and V squared over R. So anyway, that's it for today. I'll stop there before I say something stupider. Hopefully I'll come back to you Monday well.